Do you suffer from an excess of failed or scrap 3D print material? Does it keep you up at night, trying to find space for all of this junk in your attic, or your garage, or your basement? Well, what if I told you there was a way that you could turn all of this junk into valuable, reusable filament once more? Well, boy, do I have a solution for you.
Here's the answer to all the cardboard boxes of failed prints that fill your office. Introducing our DIY single screw extruder. This is for thermoplastics typically used within 3D printing such as PLA, PETG, and ABS. This is driven by a 1/2 horsepower motor connected to a 1:15 transmission. The custom-made coupling secures a standard auger bit so that torque can be transmitted through. While an extruder screw is preferred, one a similar length as the auger could easily cost $1,000. The device can be readily assembled from a parts kit and attached to any platform of suitable strength and length. For those handy, a DIY instructions can be purchased for the low cost of $20, so that all the parts needed can be fabricated yourself. This may require a 3D printer, bandsaw, mill, lathe, and power tools. The full assembly costs $1,500, which is nearly $4,000 less than a similar sized product, and just $500 more than a far smaller DIY kit. Possible upgrades include a stronger motor for additional torque so that plastic can be driven through a smaller die, more heaters to increase the melt zone, and a slower but longer cooling zone. The setup is desirable for those who have a high quantity of 3D printer waste, as this device can hold a lot of material. Once starting up the process, you can sit back and relax as you automate your recycling journey for a cleaner and greener tomorrow.
The extruder is powered by a 1/2 horsepower DC motor coupled with a 15:1 1-gear speed reducer. The main auger screw is attached to the power plant output shaft using a custom steel connecting piece bolted onto an output shaft bushing. A 1-inch steel pipe housing the auger screw will act as the main extrusion barrel. It will held onto the table by a custom-made mounting system featuring a giant aluminum block and a series of L brackets. The barrel will be heated by 2 band heaters situated near the end of the barrel. A pipe reducer at the end of the barrel will act as an agent to mount the custom-made extrusion bit.
The spooler system is completely 3D printed and has a cooling subsystem. It uses a NEMA 17 stepper motor, as well as 4 10mm 24-volt DC cooling fans and 608cc bearings. The stepper motor drives a gear system which spins the spool, but also spins a worm gear which powers an oscillator carriage. This oscillator carriage moves from right to left and guides the filament, ensuring even spooling throughout the entire process.
Our system requires a total of 21.8 amps for both our 2 power supplies and our heating elements. This does not include our 2 microcontrollers as well, which may draw up to an amp each. This requires us to utilize 2 outlets as to not blow the 20 amp circuit breaker in the building. Our 12-volt power supply is what drives our 1/2 horsepower motor, which has a stall current of 39 amps. To control the motor, we utilize a motor controller that requires a PWM signal from a microcontroller. According to reviews online, this motor controller can get really hot. As a result, we must provide a tiny wind tunnel for it, powered by fans. To protect the rest of the circuit from the motor, a 40 amp fuse was put in between the motor controller and the motor itself. Our 24-volt power supply is what drives our PID temperature controllers, which will control the temperature for us. It utilizes solid-state relays to be able to quickly switch on and off the heating elements by setting a voltage. The heating elements will simply heat up a control blade that just connects to power. For feedback, an RTT PT100 is used to record temperature, which is utilized to know the current state of the heating element. The PIDs utilize RS485 half-duplex communication, something a normal microcontroller is incapable of doing on its own. Instead, using a MAX 485 TTL to RS485 chip, we are now able to communicate with our PIDs. The PID communication line is connected to the chip using daisy chain formation, which is common practice in the industry. The 24-volt power supply also powers the 8 60mm by 60mm fans utilized in the design. It also powers the stepper motor used in the spooling process. For our spooling process, the second microcontroller is used to control the stepper motor utilizing a TMC T209. The TMC T209 allows us to control the speed, direction, and even the current draw of the stepper motor for optimal control. The TMC T209s are also known to get quite hot, so another wind tunnel is needed. For our UI control for both the extruder and spooler, 4 push buttons in conjunction with a 20x4 LCD screen is used and connected to our microcontrollers. The LCD chosen uses I2C communication for easy wiring and setup.
For our very first test, we'll be cutting up a roll of PLA filament into small pieces around 1 cm. We had also preconditioned the PLA plastic by drying it up using an oven, giving the machine the best chance of success. First, we'll dump the PLA plastic through the hopper on top of the extrusion barrel. As the plastic travels through the extrusion barrel, the plastic will be compressed and melted. Then it will come out the other side as liquidy form. 4 cooling fans placed right below the extrusion die will cool up the plastic enough so that it can get spooled up on the other side. Since this is our very first test, we'll be spooling up the filament manually to find the most desired spooling speed. In our second test, instead of using perfect case plastics, we will be using less than ideal plastic pellets. These are fail print and support structure that are either shredded manually or using the shredder created by the other team. These are plastic pellets that are more in line with the plastic that our end user will be recycling. Throughout these experiments, we have to constantly adjust the heating temperature and the spooling speed to find the most ideal setup. We found that a few degree changes on the heating element will cause a drastic different output. If the temperature is too high, the plastic will be too liquidy to pull and spool. If the temperature is too low, the plastic will be solidified before getting pushed out of the extrusion die, clogging up the extrusion path. We also found out that spooling speed had a great effect on the diameter of the spooling plastic. With a correct heating temperature and an adequate spooling speed, we are able to achieve the 1.75mm diameter filament that we desire. Thanks for watching!